Hi everybody! In this video, I will introduce to you the concept of electromagnetic energy. But first, let's talk about energy. Energy is the ability to do work or cause change. For example, we have heat energy, which heats up things. We have chemical energy, which is the energy stored between chemical bonds between substances. We have kinetic energy, or the energy that allows things to move. And then we have light energy. Now, light energy could be used to do a lot of things. We can convert light energy to heat energy to maybe heat up our homes using solar panels, or we could use light energy for our plants in order to allow our plants to grow. And plants use light energy in a reaction called photosynthesis, which allows plants to produce sugars, and that's the food that they use to survive. So, light energy is also called electromagnetic energy. Electromagnetic energy can be in the form of a wave or a massless particle called a photon. But for now, let's first focus on the definition of electromagnetic energy in the form of a wave. So in the picture below, you can see a red wave that's getting increasingly, less wide and more frequent. And this goes into the idea that waves have something called a frequency. A frequency is how frequent something happens, and in this case, the frequency for a wave is how often it repeats itself in 1 second, and that's why the unit for frequency is 1 hertz, which is also written as per second, or 1/seconds, or second to the -1 power. So you can find the frequency of a wave by seeing how many times it repeats itself. So let's start off with the edge, and let's draw the outline of the wave. And notice how once I stop at this point, it begins to, repeat and go from up, down, up, down. And this repeating unit will repeat over and over again. And the number of times this repeating unit repeats in 1 second will give you the number of hertz, or seconds to the -1. So in this picture here, let me, erase this part, and let me draw the repeating unit once more. And let's just say that this wave happened in 1 second. So since this wave has repeating patterns 3 times, and it happened in 1 second, then this wave has a frequency of 3 hertz. And that's the simple way of calculating frequency. Now let's get to wavelength. Wavelength is measured in meters because it's a type of length, and it tells us the distance between 2 crests of a wave. So for example, in this wave shown here, the crest is like the uphill, and the trough is the downhill, and the distance between 2 crests is known as the wavelength. In this picture above, the wavelength is the distance between the 2 crests, like that, and something cool is that the distance between 2 troughs is also the wavelength, since they're exactly the same thing, as you can see. And even cooler is that the distance between, the beginning and the end of a repeating pattern is also the wavelength. So wavelength can be found in many ways, but the simplest way is to look at the distance between 2 crests. Now let's look at the units for each of these. So wavelength is measured in meters, and frequency is measured in hertz. Now let's look at the symbols that represent these units. So for wavelength, we use the symbol known as lambda. Now I'm no artist, so I can't really draw the Greek letter, but it looks like that, and if you write it like that, I'm sure you'll be fine. And the symbol for frequency is V, and it's just, a V, and I kind of covered it up, but, it's a V. So now that we're done talking about that, let's talk about what this chart is showing. This chart that I put here is called the Electromagnetic Spectrum. It tells you all the different types of waves possible, and it categorizes them based on their wavelengths. So, for example, there's something called a radio wave, which is the waves that they use in radios, and these waves are typically 10 to the third meters long, or a kilometer long, so they're pretty long, but the sad thing is that they're invisible. And let's look at some other types of electromagnetic energy. Visible light is the light that we see as humans, and they're basically the colors of the rainbow as shown here. And visible light has a wavelength of around 0.5 times 10 to the negative 6 meters, so they're really small compared to radio waves. Now let's look at something even more extreme. X-rays and gamma rays typically have wavelengths that are in the magnitude of 10 to the negative 10, and it goes up to the smallest quantities like 10 to the negative 12. And let me point out something very interesting. Notice how as you decrease the wavelength and make it smaller, the frequency actually increases. And this relationship is known as an inverse relationship because as wavelength increases, frequency decreases. And in the next slide, I will show you a relationship between the two. This relationship shows the relationship between wavelength and frequency. Notice how wavelength is going to be in meters, and our frequency is going to be in hertz, or 1 over seconds, or seconds to the negative 1. And notice how we have a C constant here. Now, this C constant is the same constant that you see in E equals mc squared, which is a famous equation derived by Einstein. And C just represents the speed of light. Now, over here, the speed of light is rounded off to 3.00 times 10 to the 8 meters per second. And for this reason, the speed of light, in this case, is not an exact number, since it is measured by scientists and rounded off. So it's not an exact number because it's not exact. Now, this relationship here says that if you multiply the wavelength in meters and the frequency in hertz, then they will multiply up to 3.00 times 10 to the 8 meters per second. So notice how this is an inverse relationship since we have a constant, which is the speed of light, and this is equal to two variables that can change. And notice how k equals xy will give you an inverse relationship on a graph, and it kind of looks like this. So if I graph frequency on the y-axis and wavelength on the x-axis, it'll look like that. And it looks strikingly similar to the relationships that we derived for gas laws. Like some of the relationships, like P and V, also displayed this type of behavior. Now, let's look at the second equation. The second equation relates the frequency of a photon, and remember, a photon is a massless particle that can also represent electromagnetic energy. So think of a photon as a light particle. And this equation simply gives us the energy in a single photon given the frequency. Now, notice how there's an h. This h is also a constant measured by scientists, and it's 6.626 times 10 to the negative 34 joules times seconds. Now, we could derive the units for this, but I just did it for you because at this point, I'm sure you are well versed in finding the units for missing variables. So, notice how C and H are not exact numbers since they are measured by scientists and rounded off. and therefore they are not exact numbers, so you have to keep track of sig figs and consider those as sig figs as well. So this would have 4 sig figs, this would have 3 sig figs. And now that we're done with this, let's talk about one last thing. Make sure your units are in the one specified in red, or else it won't work. You gotta make your frequency in hertz, or 1/2. You have to make your energy in terms of joules. Your speed of light has to be in meters per second. Your wavelength has to be in meters, and such and such. So make sure your units are matching the units over here. And note that this equation calculates the energy for a single photon, so it's just one photon and not a mole of photons. So keep a note of that when you do questions that are related to these two equations. So I added the names for these constants. C is the speed of light, and H is known as Planck's constant, named after a scientist that discovered this. So let's look back at our electromagnetic spectrum. Notice how visible light is the only light that we can see, and all the other lights are lights that we cannot see. Now, knowing that fact, we can move on to another topic, and we have to talk about why X-rays and gamma rays are the most energetic. And these are the most energetic types of electromagnetic energy because they have the smallest wavelengths, which make them have the highest frequency. And according to this equation, if you have a high frequency, then you are going to have a high amount of energy. And this is exactly why X-rays and gamma rays can be dangerous to our health if we are exposed to them long enough, since they are just high energy types of energy that can literally penetrate right through us, and it's pretty dangerous, honestly. So now that we're done with that, let's try a practice problem based on the ideas we learned in this page. So calculate the energy for a mole of photons emitting green light at a wavelength of 531.64 nanometers. Now, let's do green since this is green light after all. And let's see what we should do. We know what the wavelength is, and according to the equation, if we have wavelength, then we could find the frequency. And if we can find the frequency, then we could find the energy for a single photon. And if we have the energy for a single photon, then we could probably find the energy for a mole of photons. So now that we have our thinking set in stone, let's do the problem. Our wavelength has to be in meters since this equation is in meters, and remember this note that I gave you, that all your units must be the ones specified in red in the image. So now let's convert this into meters. So 531.64 nanometers can be converted to meters by doing this, by multiplying 1 meter for every 10 to the 9 nanometers. And remember, this is part of the prefixes that you were supposed to memorize, and counts out the nanometers, and you get 531.64 times 10 to the negative 9 meters. And that's a weird negative sign, so let me rewrite that. And notice how this is not in scientific notation. We could just keep it like this, or we could just change it. So let me show you a little trick. We can convert this to scientific notation by changing this into scientific notation, and you'll see what happens. 5.3164 times 10 to the second is that, and we just have to multiply by 10 to the negative 9 meters. And if you simplify these two, you get 5.3164 times 10 to the negative 7 meters, and that's the wavelength in meters. Now we have to convert this into frequency using this equation right here. C equals lambda V. So C is 3.00 times 10 to the 8, and this is exactly equal to the wavelength, which is 5.3164 times 10 to the negative 7, and that's multiplied by our frequency. Now, doing the math, 3.00 times 10 to the 8 divided by 5.3164 times 10 to the negative 7. Make sure you put parentheses around this in your calculator, and you get that the frequency is equal to 5.643 times 10 to the 14th with 3 sig figs as shown there. And that's a weird 14. It should be a little above. So that should be 14, that should be 0. And notice how it's 3 sig figs since this has 3 sig figs and this has 5 sig figs, and we're dividing them by each other. So now that we know the frequency, we can find the energy for a single photon. So let's do that. So the energy for a single photon is equal to Planck's constant times the frequency, which is 5.643 times 10 to the 14. And doing this in your calculator, you get that the energy for a single photon with a wavelength of this is going to be 3.739 times 10 to the negative 19. What unit do we use? Oh no. Well, if you remember, this is in joules, so our answer will be in joules. And keep track of your sig figs because we are not done. This is for a single photon, so in our next page, we will write this answer, 3.739 times 10 to the negative 19 joules, and this is for a single photon, but we want it for a mole photons. So how to convert this to a mole photon so we get the energy per mole photons? Well, we have to multiply by 6.022 times 10 to the 23rd photons, and I'm going to abbreviate it there as PHO per mole of photons, and we get, well, let me just multiply it out. So 3.739 times 10 to the negative 19 times 6.022 times 10 to the 23rd, we get that per mole of photons, we have, let's see, 225,162 joules. And notice how we have 3 sig figs still, since in our previous answer it was 3 sig figs, and this has 4 sig figs, and our answer will have 3 sig figs. So let's convert this to scientific notation. This would be, let's see, I think this would actually be 2.25 times 10 to the 1, 2, 3, 4, 5 joules per mole of photons. And this is our answer. We could also write our answer in terms of kilojoules if you want, or you could even exclude the mole of photons because the answer only needed the energy, and it didn't need to say that it was for a mole of photons, but you know, it's nice to include that if you can. And that's officially our answer for this question. So let's move on to our next topic. We will now talk about emission spectrum, and emission spectrum shows us the wavelengths reflected by the atom or compound, and it's what we see because it's reflected to us. Every isotope and compound has a unique emission spectrum. So for example, for this hydrogen atom, we see that it has an emission spectrum and it's reflecting violet light, indigo light, I don't know, blue or cyan light, and red light. And for helium, it's reflecting violet, cyan, green, yellow, orange, and red light. So notice how each element has its unique emission spectrum, and Niels Bohr used the hydrogen atom to study the emission spectrum. So, I don't know why I wrote atomic spectrum, sorry, emission spectrum. And let's move on to the next topic now. So did you know that in an atom, such as this atom, with electrons flying around it, electrons can have different energy levels? Now, I didn't know this until I learned it, but now that you know, let's talk about it. N is a letter signifying the principal quantum number, or more commonly known as the principal energy level of an electron. So an electron with n equals 3 tells us that it is in the third principal energy level of an atom, since electrons can be at different energy levels, and the higher the energy level is, the farther the electron is from the nucleus. So the principal energy level ranges from 1 to infinity, and they are always whole numbers. So we typically go up to about 7 or 8, but we never go to infinity. Infinity is just something theoretical. So below, here is an equation that tells us the amount of energy there is in a mole of electrons depending on the principal energy level. And note that this equation only works for electrons in a hydrogen atom, so don't be using it for another element other than hydrogen. So this equation tells us that per mole of electrons, the energy will be negative 1313 kilojoules over the principal energy level squared the electrons are in. So let's talk about another thing. What if an electron went from one energy level to another? So if an electron goes from an energy level of n equals 2 to a higher energy level of n equals 5, the electron will have to absorb energy, and the change in energy will be positive for the electron since the electron is gaining energy, so it's adding energy. Now, what if an electron went from a higher energy level to a lower energy level, such as from 5 to 2? Then it will go down in terms of energy, and it will lose energy, so the change in energy will be negative. So in other words, the electron will be releasing energy in the process. To find the change in energy associated with these processes, we can use this equation here that tells us that for a mole of electrons, the change in energy, this triangle means change, and it's known as delta. So delta E, or the change in energy, is equal to the energy for a mole of electrons in their final state minus the energy for a mole of electrons in their initial state. So both of these will come from here, obviously, but the n will be different for both of them. And depending on whether the final principal energy level is higher or lower than the initial principal energy level, that will determine the sign on delta E. So if you're going from 2 to 5, then you are absorbing energy, so delta E will be positive. And if you're going from 5 to 2, then you are losing energy, so delta E will be negative. So you might be wondering, why is the energy for a mole of electrons negative since, n is going to be positive? So I will explain this, but it's a bit complicated. And if you aren't curious about this, or if it gets too complicated for you, feel free to skip it. So why is the energy of an electron negative? So here below I have 3 notes written in blue, and these notes are for you because I am assuming that my audience isn't that well versed into advanced physics, and these topics were probably never covered in your middle school classes. So I am covering it here, and try to understand it if you can. So if something absorbs energy, it is gaining positive energy, and if something releases energy, it is losing energy, which indicates a negative sign. So I've talked about this already. Let's look at our second note. The total energy is equal to the potential energy and the kinetic energy added up. So what is potential energy? Well, potential energy comes from the attraction between objects. So for example, we standing or sitting have a gravitational potential energy because we are attracted to the Earth, and thus we have some sort of potential energy due to gravity because we are attracted, and gravity is, an attractive force. And if an object is not attracted to anything, it has a potential energy of 0. So let's move back to the second point. Kinetic energy is always positive. Potential energy can be either positive or negative depending on what you define as 0. But in the case of an electron, it will be negative, as I will prove below, since we are assuming the potential energy is 0 for no attraction. So the energy of an electron is negative, since if we assume that the potential energy of an electron not attracted to anything is 0, so I can draw an electron not attracted to anything, the potential energy is 0, then we can deduce a few things. If an electron is attracted to the atom, so if an electron is attracted to an atom and going around it, inside an orbital possibly, then it must either have a positive or negative potential energy. In order to escape the atom and have a potential energy of 0, it needs to absorb some energy to do that. So if it wants to escape, it has to absorb some energy. Therefore, the potential energy of an electron and an atom must be negative, since a negative potential energy plus whatever energy it absorbs will equal to the potential energy when it is not attracted to anything, 0. Despite the electron in an atom having some kinetic energy, since it is moving after all, the potential energy is so negative that it makes the overall energy negative. You can think of an electron as a spaceship trying to escape Earth's gravity, and once it escapes, it will have a potential energy of 0. So, sorry if you didn't understand that, but I mean, I don't think you have to understand this, but this is just for anyone who's curious. Next part, we have to answer this question. Find the change in energy for an electron going from n equals 2 to n equals 6 in a hydrogen atom. Then calculate the wavelength of the proton that was absorbed by this electron. So what's happening is that this one electron wants to go from n equals 2 to, n equals 6, which is a higher energy level, and it has to absorb some sort of light, and in this case, it's a photon, so I'm going to write the photon in red, and this photon will crash into the electron and give it some energy to move it up. And we just have to calculate the wavelength of that proton that bumps into that electron. So when an electron absorbs a photon, it moves up in energy levels. When an electron moves down energy levels, it releases a photon. So in this case, it moves up, so it's absorbing a photon. Now let's find the energy change for an electron going from n equals 2 to n equals 6, using this equation right here as well as that. So what will happen is that we have to find the change in energy for a mole of electrons going from 2 to 6 first. So we have to find the energy associated with the final state, which is in the equation for final. And the final state is when n equals 6, so I think it's negative 1313 kilojoules per 6 squared, and then we have to subtract that by our initial state, which is n equals 2, negative 1313 kilojoules per 2 squared, and doing the math we get En, let me write the delta there actually, is equal to negative 291.8 kilojoules per mole of electrons. But we need it for 1 electron, so we are going to do it for 1 electron, and on the next page I will show you that. So after doing some calculations on the screen, I found that the change in energy for 1 electron when it goes from n equals 2 to n equals 6 is 4.85 times 10 to the negative 19 joules. So now that we know that, we know from this question that an electron needs to absorb a photon with exactly this amount of energy in order to, move from 2 to 6. So let's find the wavelength for this proton with this energy, because 1 photon will excite 1 electron, and this electron needs this much energy from the photon. So we have to find a photon that has this energy. So on the next page, I'll do that. So what I did here was that I took the energy that that 1 electron needed to move from n equals 2 to n equals 6, and this is the energy that that photon needed in order to cause the electron to jump from 2 to 6. So this is the energy that the photon needs to do that, and I set it equal to Planck's constant times the frequency, got frequency, then used the frequency to find the wavelength, which turned out to be 4.10 times 10 to the negative 7 meters, and this corresponds to the wavelength for violet light. So for this 1 electron to move from n equals 2 to n equals 6, it needs a wavelength of, I guess, about 4.10 times 10 to the negative 7 meters in order to cause this change to happen. So the next topic we will talk about is the Bruy wavelength. This idea comes from the fact that objects have wave-like properties according to quantum theory. However, it is only observable in very small objects like an electron. Therefore, something like an electron can behave as a wave and as a particle. This is called wave-particle duality. So, the Bruy wavelength can be calculated using this equation over here, which gives us the Bruy wavelength in meters, and it is equal to Planck's constant. Remember, Planck's constant is 6.626 times 10 to the negative 34 joules times seconds, divided by mass times velocity. Now, mass is in kilograms and velocity is in meters per second. And something you might learn if you ever take physics is that mass times velocity is also known as linear momentum, or just momentum for simplicity. And let's do an example problem using this equation. Find the Bruy wavelength associated with a person who is 60 kilograms running at 7 meters per second. So using Bruy's equation, let's do that. So the wavelength is equal to Planck's constant, 6.626 times 10 to the negative 34, divided by the momentum, which is the mass, 60, times the velocity, which is 7. And notice how this is in kilograms and this is in meters per second, and these units match up, so we're doing great so far. And we get that the Bruy wavelength is going to be 1.5776 times 10 to the negative 36 meters. And if you really want to use sig figs, then we have to really round this up, and we have to say that it's equal to 2 times 10 to the negative 36 meters. And that is the Bruy wavelength for a person who is 60 kilograms running at 7 meters per second. So I wanted to talk about one last thing. This has to do with the energy levels that we discussed before, and this is for hydrogen atoms, so negative 1313 kilojoules per the principal energy level squared, and this defines the energy at each level. So I calculated it for n equals 1 all the way to n equals 4, and notice how the energy goes from negative 1313 to negative 328 to negative 146 to negative 82, and if you make n big enough, or when you make n approach infinity, then the bottom will become so large that eventually the top won't matter anymore, and the answer will be very, 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 very close to 0. So this goes to prove that as you go up, you are increasing in energy and becoming less negative and approaching 0. And this also shows that the distance between energy levels closes in. So at the beginning, the distance is quite large, but as you get into higher and higher energy levels, the energy of the electron gets increased by a smaller and smaller and smaller amount. And this happens until the energy of the electron is equal to 0. So this kind of proves how the potential energy of an electron is at first negative, and as you put more energy into it and move it up, it has to absorb energy, and it absorbs energy so that it can get as close as possible to 0, which is the point at which n equals infinity, and that's the point at which the electron will no longer be attracted to the atom and will be so far, far away that it's basically not attracted, and things that aren't attracted have a potential energy of 0. So, one last thing, but just because the energy of an electron is 0 doesn't mean that it has no energy, because if that's true, then what does it mean to have negative energy, right? Remember, this scale is all relative. And having a more negative energy means that you have lower energy, and having a less negative energy means that you have more energy, since you have to add energy to a more negative number to make it a less negative number. So this here has more energy than this. So that's just some misconceptions that might come up. But remember, this scale is not typically what you think of when you think of energy. You think of energy as something that's positive, but that is assuming that no energy is equal to zero. But in the diagram over here, when we say that the energy is zero, we mean that it has so much energy that it is not attracted to the atom anymore. So anything below it will have less energy, and the zero standard we put here is the minimum energy needed for the electron to have n equals infinity, or in other words, be located so far away from the atom that it's not attracted to the atom anymore. So be careful about that, and that's all for this video, and have a nice day.